Hello, today I want to present to you my DMA hash map idea. So for that, let's talk about this function here. This is DMA sample data. The purpose of this function is that if you play a note in Mario 64, you can call this function and you supply it a ROM address and a size of how much data you need. And then it will use this information to try to give you the data for the note with as little data throughput as possible. So our goal here is to reduce memory traffic as much as possible. Now, what Nintendo does is they provide an arc2. The arc2 means if this is 1, then just try to find an existing DMA that fits, and they provide an index reference. Now, an index reference is interesting in how it works. Each note, when it plays and it finds a sample buffer, it gets assigned an index reference to that sample buffer. So this is kind of a useful structure. Let me talk you through what this does real quick so we can understand the problems with it. So first, let's assume this is our first node we play in the game. Arc2 is going to be set to 1 because when a new node starts, it's always going to be set to 1 because we need to find a new buffer. Now, it iterates through a shit ton of sample DMAs here. Then it checks if the sample DMA already has valid data. If it does have valid data, it gets moved out of some reuse queue, which we don't care about that. It gets marked as this needs to stay valid for 60 audio ticks. The reference gets assigned to this buffer and we just return it. So doing this, we do have a shit ton of memory reads because we do this all, but we can point to the sample without having to load new data from ROM. That's great. Then what happens afterwards? Well, afterwards we still need to DMA data. So we just take our index, we get the sample DMA that belongs to it. We check if it has valid data. If it does have valid data, then we mark it here as not overridable. We mark it as valid for 2 ticks only. Not sure why only 2, but that is what we do. And then return the address. Now, if there is no valid address yet, which of course happens if there's no valid address here or no valid address here, then we just mark it as having to do a DMA. When we have to do a DMA, we load the data from ROM into RAM. So far so good. Of course there is a few issues with this. The most obvious one is, well, this is a huge iteration. Do you want to do this every time when you play a note? And this happens quite a bit. The second issue is, well, okay, you have your DMA, but what if it's a larger node? And now the larger node goes, you know, out of this range. You can't do this. You're gone. And then it needs to assign a new one. And it might discard the old data because there's only so many buffers. So when I tested this in Vanilla Mario 64 in my course 3, when I was playing the song, up to 9 DMAs per frame happened, which is I mean, it's not that much, but it does interrupt the audio thread over and over, which means we have a lot of thread switches going on, and that means we have to load a lot of data from ROM, which they're each around 0x80 in size, so we are loading around 0x480 data at most. It's not terrible, but I also don't like it. And the thing that bothers me the most actually about this is something I barely talked about yet, which is the TTL here. This is, I think this stands for time to live. I don't know why they called it like this, but I imagine that's what it is. Now, if you look at this, TTL, we have all of this stuff. We have all these TTLs ticking, and then we have all of this stuff and all of these TTLs ticking. DMA num sample. This I think is like 200 entries. Why this is split into 2 parts, I am not sure, the sample list size. Because just from looking at this, it looks like the TTLs for the first list do not even do anything. Either way, 9 loads is quite a bit. I managed to reduce this to at most 1 load. How does this work? Well, with a hash map. Obviously you use a hash map instead of iterating, right? Like that is just common sense. So what we do is we get a ROM address, we get a current offset as an offset into the current instrument we're playing, and we get a size. Now we are rounding this down so that we can load from any offset without it getting weird. We use this as an entry into our hash map here. Num sample hashes is a nice round number, 0x100. Then we have like, okay, well, if one DMA buffer is too big, then we just send you to the dodge buffer shadow realm, which these guys can handle anything. These only exist for 1 tick and then become invalid because these are supposed to never be used, and in practice they are basically never used except for some extreme circumstances. If our ROM address exists on a hash map, which by the way this is just one lookup, instead of having to iterate all those things, we just return that. Then each hash also has a collision dodge entry. I decided that my hash map would only be able to handle 2 values with the same hash at a time, because more than that is overkill. Yes, technically it is correct to handle an unlimited amount of them, but that is slow as hell. So I just said, well, we only handle 2, and if a 3rd collision happens, that's right, I send you to the dodge buffer shadow realm. Then instead of having TTLs that take every frame, which is insane, that cost probably like 150 microseconds in vanilla, we just store the last VI that this was used on. A VI is a vertical interrupt, so this increases at 60 frames a second, meaning every frame this increases by 1. And if the current VI is too large, much larger than the current one, then when you last used this, well, you're an old entry, we're gonna kick you out. Get overwritten, idiot. Same with the collision dodge entry. So yeah, doing this keeps instruments data around as long as we want. We do not have to manage these reuse queue, reuse tails. We do not have to manage TTLs. We don't have to iterate over the whole thing. And this reduces it from like up to 9 misses to up to 1 miss. That means that the entire data throughput to mix the sound is halved when we hit one of these sample hash maps. Actually, it's more than halved because we don't need to iterate the entire for loop here. So it is more than halved. This is probably like the largest number of data throughput on this whole thing. How big is this? Let me just see. How big is this? What's the difference in size here? I think these are done with ++. Max simultaneous nodes. Well, that looks like it's only a difference of 16. Wait, so there's only one of these per node? I didn't even know that. That is nasty. So what if you have like a sample that's long? You're just gonna get kicked out like instantly? Oof, yeah, that explains why it's up to 9. Yikes. Anyway, that's my idea. If you guys see any improvement to my idea, let me know, please. But I think this is pretty close to optimal. Bye.